Chapter 7, Logarithms. Okay, so logarithms is a way to approach or explore accessing just the exponent values on it. In this case, they want us to write the equation in logarithmic form. So what we want to do is we want to notice that we have a base of 12. That's our base value. We have a power value of 2, and then this is our other value, what it equates to in a regular number. So when we take the log, we're going to take the log of both sides. We're going to do log base 12 of this, and then here, log base 12 of that. So when we write it out, log base 12 of 12 squared, we get on the other side log base 12 of 144. Okay. From here, we can evaluate this log, and our shortcut rule is we can say, hey, if the log of a certain base, if the bases are the same, we can say that's equivalent to whatever power value it is. So if the bases are the same, your answer is going to be this. So you can replace all of that with just what the power value is. In this case, our exponent, or power value here, is going to be 2. So we can write this as log base 12 of 144. Now there's not a real easy way to check this directly on our calculator. We'd have to do what's called a change of base. And to do that, we'd write it in 2 different log equations. We'd do a log base 10 of the 144, the value inside the parentheses, divided by a log base 10 of what the base value is. And if you plug this into your calculator, you'll get the same value of 2. So on our calculator here, if we do log 144 divided by log of 12, we'll get the 2 value out. Okay. But our answer in this case is this. This is what we're wanting to show. Question number 2, write the equation in logarithmic form. So we're going to work through the same setup here. Notice that our base is a 5. So we will write log base 5 of 5 to the negative 3 equals log base 5 of 0.008. Realizing that our bases are the same, and so we can extract the power. Negative 3 equals log base 5 of 0.008. We can check our work on a calculator by taking on this side log base 10 of 0.008 over log base 10 of 5. And that's going to get negative 3 for our answer. On the calculator, we can verify it. So log base 10 of 0.008 divided by log base 10 of 5. And we get a negative 3 for our result. Okay, number 3 asks us to write the equation in exponential form. So we're working kind of backwards on it. We're going to try and rewrite this or reevaluate it on both sides. We notice that we have a base of 3 that we're using. So we can basically take this equation and make these the powers. And we'll take a 3 to the power of this, log base 3 of 729 equals 3 to the 6th power. These values here, the 3 to the log of this, cancel out, and we're left with just what's inside the parenthesis here. We get 729 equals 3 to the 6th power. And we can verify that on our calculator. 3 to the 6th power, we get 729. So our key indicators here, this is the answer that they're looking for. Our indicators here are the base here, and realizing from our previous example that if we have a log to a certain base, if we have that base to a power, then our power value comes out. And this is what we're starting out with from it. Number 4. So notice we're going to write it in exponential form. We've got the 1/2 power. So we're going to take 1/2 to the log 1/2 of 8 power equals 1/2 to the -3 power. These things cancel out and we're left just with the 8. So 8 equals 1/2 to the -3 power. And we can verify that. 1/2 to the -3rd power, and we get 8. Okay, number 5, they want us to write it in exponential form. Notice here that they don't have any number written by the log. We assume that base is a 10. So we can take 10 to the log of 100 power equals 10 to the 2 power. This cancel out and we get 100 equals 10 squared. And to prove it, 10 squared is indeed 100. Okay, so this time instead of using a log base, they want us to use the natural log. And so our natural log equates to the e to the x. Those are our inverses. So where we did log with a base of 10 and our alternate power, we take that base and put it here. When we do ln, our alternate piece is doing e, the natural log equivalent. So in this case, we're going to take e to the ln of 5, and we'll have that's going to be approximately equal to e to the 1.6094. And here e and ln cancel out, and so we get 5 is approximately e to the 1.6094. And we can check that in our calculator. We can take e to the 1.6094, and 4.9998 rounds up or is equivalent, rounding to 5. Okay, number 7. They want us to calculate the log of 144, and we're going to round to 4 decimal places. So we'll do log 144. We enter that in, and we get 2.158362492. We're going to round to 4 decimal places. So this here goes up, and we get 2.1584. Using the calculator, we are going to do the similar equation, but now we're going to add a 0 to the end, make it a 10 times bigger. And notice our result here is 3.158362492. We're rounding to 4 decimal places. So looking here, we go up and we get 3.1584. Notice the difference between this and the last value. We are 10 times bigger for our value inside of the log, and when we evaluate it, we're one whole unit factor bigger. All right. Log of 225, and we get 2.35 21 825 18. We're rounding to 4 decimal places, so 1, 2, 3, 4. it goes up 2.3522. And if we evaluate the next one at a 0, we get 3.352182518. We're rounding to 4 decimal places, and this bumps it up, so 3.3522. Notice when we're a factor of 10 bigger, we're 1 bigger on the whole unit scale. Okay, here they ask us to use the anti-log. So the anti-log is 10 to the value inside of here. In this case, we're going to get 1,000 on the calculator. The anti-log, you just hit second log. Notice that's our anti-log button, and we'll put in 3, and we get our 1,000. 2 decimal places, we would put our zeros on there for precision. Anti-log of 1.5. We get 31.6227.766. We're going to 2 decimal places, and because of this we just drop the rest, so 31.62. The anti-log of 2.5, $316.227.766. 2 decimal places again, we're going to bump it up, 316.23. And so realize when you have a value of 1 difference here in your anti-log, you're a full place movement over a. Okay, our anti-log of 1.6990. And on here we get 50.0034535. We're rounding to 2 decimal places, and so we get 50.00. Okay. On problem number 15, we have an output and an input. It's in watts, and so we are going to use the equation 10 times the log of the output over the input, and that equals our value in decibels. So in this case, we can plug in our values. We've got, so 10 log, our output is 12.5 watts over our input of 27.3 watts. So we realize what we get out is less than what we put in, so our decibel should be a negative value when we get done with it. On our calculator, we can do 10 log 12.5 divided by 27.3, and we get a value of negative 3.39252634. We want it to the nearest tenth, so our nearest tenth becomes negative 3.4 for our value. And the unit's decibel. On number 16, we have a antenna that has a gain, and if the output power is 20 microwatts, what's the input power? So we're going to write our equation, our 13.7 decibels equals 10 times the log of the output, so 102 over the input, and I'm going to call it x, and we are going to solve for this. We're going to divide both sides by 10, so we get 1.37 equals log of 102 over x. We are going to do the anti-log, so we'll do 10 to the power, 10 to the power. The logs cancel out, and so we get 10 to the 1.37 equals 102 over x. We can cross multiply and re-evaluate here, so we get x times 10 to the 1.37 power equals 102, divided by the 10 to the 1.37. We get x equals 102 divided by 10 to the 1.37 power. And that we have to plug into our calculator. So if we take 102 divided by 10 to the 1.37 power, and we get the value of 4.35111, and if we're rounding to the nearest hundredth, so 4.35111, our hundredths here, 4.35 for our result. That is the end of chapter 7.